This two-year course in physics is presented from the point of view that you, the reader, are going to be a physicist. This is not necessarily the case, of course, but that is what every professor in every subject assumes. If you are going to be a physicist, you will have a lot to study. 200 years of the most rapidly developing field of knowledge that there is. So much knowledge, in fact, that you might think that you cannot learn all of it in 4 years. And truly you cannot. You will have to go to graduate school too. Surprisingly enough, in spite of the tremendous amount of work that has been done for all this time, it is possible to condense the enormous mass of results to a large extent, that is, to find laws which summarize all our knowledge. Even so, the laws are so hard to grasp that it is unfair to you to start exploring this tremendous subject without some kind of map or outline of the relationship of one part of the subject of science to another. Following these preliminary remarks, the first 3 chapters will therefore outline the relation of physics to the rest of the sciences, the relations of the sciences to each other, and the meaning of science to help us develop a feel for the subject. You might ask why we cannot teach physics by just giving the basic laws on page 1 and then showing how they work in all possible circumstances, as we do in Euclidean geometry, where we state the axioms and then make all sorts of deductions. So, not satisfied to learn physics in 4 years, you want to learn it in 4 minutes. We cannot do it in this way for 2 reasons. First, we do not yet know all the basic laws. There is an expanding frontier of ignorance. Second, the correct statement of the laws of physics involves some very unfamiliar ideas, which require advanced mathematics for their description. Therefore, one needs a considerable amount of preparatory training, even to learn what the words mean. No, it is not possible to do it that way. We can only do it piece by piece. Each piece, or part of the whole of nature, is always merely an approximation to the complete truth, or the complete truth so far as we know it. In fact, everything we know is only some kind of approximation, because we know that we do not know all the laws as yet. Therefore, things must be learned only to be unlearned again, or more likely, to be corrected. The principle of science, the definition almost, is the following. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. But what is the source of knowledge? Where do the laws that are to be tested come from? Experiment itself helps to produce these laws in the sense that it gives us hints, but also needed is imagination to create from these hints the great generalizations, to guess at the wonderful, simple, but very strange patterns beneath them all, and then to experiment to check again whether we have made the right guess. This imagining process is so difficult that there is a division of labor in physics. There are theoretical physicists who imagine, deduce, and guess at new laws, but do not experiment, and then there are experimental physicists who experiment, imagine, deduce, and guess. We said that the laws of nature are approximate, that we first find the wrong ones, and then we find the right ones. Now how can an experiment be wrong? First, in a trivial way, if something is wrong with the apparatus that you did not notice. But these things are easily fixed, and checked back and forth. So without snatching at such minor things, how can the results of an experiment be wrong? Only by being inaccurate. For example, the mass of an object never seems to change. A spinning top has the same weight as a still one. So a law was invented. Mass is constant, independent of speed. That law is now found to be incorrect. Mass is found to increase with velocity, but appreciable increases require velocities near that of light. A true law is, if an object moves with a speed of less than 100 miles a second, the mass is constant to within 1 part in a million. In some such approximate form, this is a correct law. So in practice, one might think that the new law makes no significant difference. Well, yes and no. For ordinary speeds we can certainly forget it, and use the simple constant mass law as a good approximation. But for high speeds we are wrong, and the higher the speed, the more wrong we are. Finally, and most interesting, philosophically we are completely wrong with the approximate law. Our entire picture of the world has to be altered, even though the mass changes only by a little bit. This is a very peculiar thing about the philosophy, or the ideas behind the laws. Even a very small effect sometimes requires profound changes in our ideas. Now, what should we teach first? Should we teach the correct but unfamiliar law with its strange and difficult conceptual ideas, for example, the theory of relativity, four-dimensional space-time, and so on? Or should we first teach the simple constant mass law, which is only approximate but does not involve such difficult ideas? The first is more exciting, more wonderful, and more fun, but the second is easier to get at first and is a first step to a real understanding of the first idea. This point arises again and again in teaching physics. At different times we shall have to resolve it in different ways, but at each stage it is worth learning what is now known, how accurate it is, how it fits into everything else, and how it may be changed when we learn more. Let us now proceed with our outline, or general map of our understanding of science today, in particular, physics but also of other sciences on the periphery, so that when we later concentrate on some particular point, we will have some idea of the background, why that particular point is interesting, and how it fits into the big structure. So, what is our overall picture of the world? 1-2 Matter is made of atom. If in some cataclysm, all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generations of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, or the atomic fact, or whatever you wish to call it, that all things are made of atoms, little particles, that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world, if just a little imagination and thinking are applied. Chapter 1:1. To illustrate the power of the atomic idea, suppose that we have a drop of water, a quarter of an inch on the side. If we look at it very closely, we see nothing but water, smooth, continuous water. Even if we magnify it with the best optical microscope available, roughly 2,000 times, then the water drop will be roughly 40 feet across, about as big as a large room, and if we looked rather closely, we would still see relatively smooth water, but here and there small football-shaped things swimming back and forth. Very interesting. These are paramecia. You may stop at this point and get so curious about the paramecia with their wiggling cilia and twisting bodies that you go no further, except perhaps to magnify the paramecia still more and see inside. This, of course, is a subject for biology, but for the present, we pass on and look still more closely at the water material itself, magnifying it 2,000 times again. Now the drop of water extends about 15 miles across, and if we look very closely at it, we see a kind of teeming, something which no longer has a smooth appearance. It looks something like a crowd at a football game, as seen from a very great distance. In order to see what this teeming is about, we will magnify it another 250 times, and we will see something similar to what is shown in Fig 3. This is a picture of water magnified 1 billion times, but idealized in several ways. In the first place, the particles are drawn in a simple manner, with sharp edges, which is inaccurate. Secondly, for simplicity, they are sketched almost schematically in a two-dimensional arrangement, but of course they are moving around in 3 dimensions. Notice that there are 2 kinds of blobs or circles to represent the atoms of oxygen, black and hydrogen white, and that each oxygen has 2 hydrogens tied to it. Each little group of an oxygen with its 2 hydrogens is called a molecule. The picture is idealized further, in that the real particles in nature are continually jiggling and bouncing, turning and twisting around one another. You will have to imagine this as a dynamic rather than a static picture. Another thing that cannot be illustrated in a drawing is the fact that the particles are stuck together, that they attract each other. This one pulled by that one, etc. The whole group is glued together, so to speak. On the other hand, the particles do not squeeze through each other. If you try to squeeze 2 of them too close together, they repel. The atoms are 1 or 2 becquerel centimeters in radius. Now 10^8 centimeters is called an angstrom, just as another name. So we say they are 1 or 2 angstroms and at in radius. Another way to remember their size is this. If an apple is magnified to the size of the Earth, then the atoms in the apple are approximately the size of the original apple. Now imagine this great drop of water with all of these jiggling particles stuck together and tagging along with each other.
The water keeps its volume, it does not fall apart because of the attraction of the molecules for each other. If the drop is on a slope, where it can move from one place to another, the water will flow, but it does not just disappear. Things do not just fly apart because of the molecular attraction. Now the jiggling motion is what we represent as heat. When we increase the temperature, we increase the motion. If we heat the water, the jiggling increases and the volume between the atoms increases. And if the heating continues, there comes a time when the pull between the molecules is not enough to hold them together, and they do fly apart and become separated from one another. Of course, this is how we manufacture steam out of water. By increasing the temperature, the particles fly apart because of the increased motion. Chapter 1.2. In Fig 1.2.2, we have a picture of steam. This picture of steam fails in one respect. At ordinary atmospheric pressure, there certainly would not be as many as 3 water molecules in this figure. Most squares this size would contain none, but we accidentally have 2.5 or 3 in the picture, just so it would not be completely blank. Now in the case of steam, we see the characteristic molecules more clearly than in the case of water. For simplicity, the molecules are drawn so that there is a 120 degree between the hydrogen atoms. In actual fact, the angle is 105 degree 3, and the distance between the center of a hydrogen and the center of the oxygen is 0.957 Al2. So we know this molecule very well. Let us see what some of the properties of steam vapor or any other gas are. Imagine a room with a number of tennis balls, 100 or so bouncing around in perpetual motion. When they bombard the wall, this pushes the wall away. Of course we would have to push the wall back. This means that the gas exerts a jittery force which our coarse senses, not being ourselves magnified a billion times, feel only as an average push. In order to confine a gas, we must apply a pressure. Figure 1.3 shows a standard vessel for holding gases, used in all textbooks, a cylinder with a piston in it. Now it makes no difference what the shapes of water molecules are, so for simplicity we shall draw them as tennis balls, or little dots. These things are in perpetual motion in all directions. So many of them are hitting the top piston all the time, that to keep it from being patiently knocked out of the tank by this continuous banging, we shall have to hold the piston down by a certain force, which we call the pressure. Really, the pressure times the area is the force. Clearly the force is proportional to the area, for if we increase the area but keep the number of molecules per cubic centimeter the same, we increase the number of collisions with the piston in the same proportion as the area was increased. Chapter 1.3. Now let us put twice as many molecules in this tank, so as to double the density, and let them have the same speed, i.e. the same temperature. Then to a close approximation, the number of collisions will be doubled, and since each will be just as energetic as before, the pressure is proportional to the density. If we consider the true nature of the forces between the atoms, we would expect a slight decrease in pressure because of the attraction between the atoms, and a slight increase because of the finite volume they occupy. Nevertheless, to an excellent approximation, if the density is low enough that there are not many atoms, the pressure is proportional to the density. We can also see something else. If we increase the temperature without changing the density of the gas, i.e. if we increase the speed of the atoms, what is going to happen to the pressure? Well, the atoms hit harder because they are moving faster, and in addition they hit more often, so the pressure increases. You see how simple the ideas of atomic theory are. Let us consider another situation. Suppose that the piston moves inward, so that the atoms are slowly compressed into a smaller space. What happens when an atom hits the moving piston? Evidently it picks up speed from the collision. You can try it by bouncing a ping-pong ball from a forward-moving paddle, for example, and you will find that it comes off with more speed than that with which it struck. Special example: if an atom happens to be standing still and the piston hits it, it will certainly move. So the atoms are hotter when they come away from the piston than they were before they struck it. Therefore all the atoms which are in the vessel will have picked up speed. This means that when we compress a gas slowly, the temperature of the gas increases. So under slow compression, a gas will increase in temperature, and under slow expansion it will decrease in temperature. Chapter 1.4. We now return to our drop of water and look in another direction. Suppose that we decrease the temperature of our drop of water. Suppose that the jiggling of the molecules of the atoms in the water is steadily decreasing. We know that there are forces of attraction between the atoms, so that after a while they will not be able to jiggle so well. What will happen at very low temperatures is indicated in Fig 1.4. The molecules lock into a new pattern, which is ice. This particular schematic diagram of ice is wrong because it is in 2 dimensions, but it is right qualitatively. The interesting point is that the material has a definite place for every atom, and you can easily appreciate that if somehow or other we were to hold all the atoms at one end of the drop in a certain arrangement, each atom in a certain place, then because of the structure of interconnections, which is rigid, the other end miles away at our magnified scale will have a definite location. So if we hold a needle of ice at one end, the other end resists our pushing it aside, unlike the case of water, in which the structure is broken down because of the increased jiggling, so that the atoms all move around in different ways. The difference between solids and liquids is, then, that in a solid the atoms are arranged in some kind of an array, called a crystalline array, and they do not have a random position at long distances. The position of the atoms on one side of the crystal is determined by that of other atoms, millions of atoms away on the other side of the crystal. Figure 1.4 is an invented arrangement for ice, and although it contains many of the correct features of ice, it is not the true arrangement. One of the correct features is that there is a part of the symmetry that is hexagonal. You can see that if we turn the picture around an axis by 60 torrs, the picture returns to itself. So there is a symmetry in the ice which accounts for the 6-sided appearance of snowflakes. Another thing we can see from figure 1.4 is why ice shrinks when it melts. The particular crystal pattern of ice shown here has many holes in it, as does the true ice structure. When the organization breaks down, these holes can be occupied by molecules. Most simple substances, with the exception of water and type metal, expand upon melting because the atoms are closely packed in the solid crystal, and upon melting need more room to jiggle around. But an open structure collapses, as in the case of water. Now, although ice has a rigid crystalline form, its temperature can change. Ice has heat. What is the heat in the case of ice? The atoms are not standing still, they are jiggling and vibrating. So even though there is a definite order to the crystal, a definite structure, all of the atoms are vibrating in place. As we increase the temperature, they vibrate with greater and greater amplitude until they shake themselves out of place. We call this melting. As we decrease the temperature, the vibration decreases and decreases until at absolute zero, there is a minimum amount of vibration that the atoms can have, but not zero. This minimum amount of motion that atoms can have is not enough to melt a substance with one exception, helium. Helium merely decreases the atomic motions as much as it can, but even at absolute zero, there is still enough motion to keep it from freezing. Helium, even at absolute zero, does not freeze, unless the pressure is made so great as to make the atoms squash together. If we increase the pressure, we can make it solidify.